the slides up here. Hello again, I'm back. Another 20 minutes of me and then you won't see me again. Yeah, so a very different topic this time, autonomous cyber defense. I'm going to try and give a general introduction first, just for anyone that's kind of unfamiliar with this area, to do a bit of scene setting, and then I'll go into the specific work that we've done on contextual reinforcement learning for autonomous cyber defense. So autonomous cyber defense, it does what it says on the tin. You are trying to build an AI agent that can defend a cyber network. And by cyber network, we just mean a collection of nodes, which will consist of PCs, servers, switches, etc., and the links that connect all of those things together. And the AI agent to defend this network has to observe the current state of the network and any operational context that sits around that, and then use that operational context to decide on actions to take on the network to both prevent and mitigate attacks when they happen, and then eventually recover the network after the attacks as well. And kind of the motivation for doing this is it holds a lot of promise for doing cyber defense at machine speed and at a scale that we just can't achieve with human operators. Within this, there's kind of three main tasks that you can think about. So maintenance of the network when it's not under attack, detection of attacks when they do happen, and then finally response and recovery from attacks. So in this talk, I'm going to focus on two bits, the maintenance and response, because detection's a slightly different task, which is best not done with agents in most cases. And what does this actually look like? Typically, you've got your agent, which is this cute little robot here, and then your environment, which consists of your cyber network and the transition dynamics associated with that. So the transition dynamics is, if I'm in state S and take action A, what's the probability I end up in state S prime? And the agent observes the environment through an interpreter, which takes kind of the raw environment state and turns it into an observation which is suitable for the agent. Agent picks an action that's applied to environment, it updates, and then you do this over and over again if everything's going well many times a second across your network. Then reinforcement learning is just this loop, but you add a reward during training, which tells you how good the current state is, and the agent's goal is to try and maximize that reward over the long term. So that's reinforcement learning. Applying that to cyber defense, it turns out it's really very hard to do well for many, many, many reasons. Here are some of my favorite. I can't go through all of these today, but if you're interested in talking about this, then I'm more than happy to talk through it with you afterwards. Today, we'll just focus on three of them, which are dynamic threat intelligence. So in this case, you really are competing against someone who is making or doing their best efforts to mess with you and your system. So they can do things that will intentionally try to break your system. So your agent needs to be able to adapt to these kind of unseen challenges. Second, there's varying system requirements across any network that you want to deploy on, and these system requirements can change during deployment as well at any time. And then very similarly, mission objectives. So this is a little bit more defense terminology, but the agent or the network is there for a reason. You're trying to achieve something by having that network there, which is your mission. And that can change between deployments and during deployments as well. So just to give a simple example of why this is hard, here's a very, very basic case. You have a network which consists of a convoy, which is connected via a lead vehicle to a home base. If that lead vehicle gets taken out of the network for whatever reason, such as an attack, then the agent will need to add a new connection from the base to a new lead vehicle and update the connections within that network. All of the connections which exist on the right-hand side are critical for delivering the mission after the attack, but before the attack, they are like the exact wrong thing to do. So you need to be able to adapt to all of these changes live on the go. And this is a thing that traditional standard approaches to autonomous cyber defense struggle with. They just take the network state as an observation, and they don't have this kind of surrounding operational context to make their decisions on. That's because that information is complicated and really hard to encode. And therefore, you learn kind of a policy as an agent that only acts on the observations that you see, which means it can't adapt to this kind of operational context. And that's what we're trying to resolve in this work. And just to contrast to how a human operates, they operate primarily on this operational context. They take the system requirements of threat intelligence and mission objectives and apply that to their specific problem rather than the other way around. And that lets them do adaptive prioritization, on-the-fly balancing of these system requirements, threat intelligence, and mission objectives to decide on actions. And when those things change, the operational context changes, they can quickly adapt to that. Okay, so to bridge this gap between the agents, we've introduced this contextual RL framework where the external data sources are fed into an information generator, which combines that information with the observation from the cyber environment, standard observation you get in autonomous cyber defense, and combine it into a contextualized observation and reward. And this adds a layer of abstraction between the core agent and this kind of processing of operational context. And this lets us kind of do a lot of the difficult, expensive processing away from the core agent. Yeah, you might be wondering, why do we not just do this all inside the agent? Everyone loves a bit of end-to-end ML. But the reason is that the agent needs to be able to act very quickly, probably many, many times a second on a real network, and potentially might be distributed across a network with many instances running in parallel. If you had to process all of this information inside that agent at every time step, it would become very slow and expensive to scale this. So to give some examples of this, system requirements might be things like config files, SLAs. These are generally fairly large, semi-static, might have natural language in them, will vary a lot between different systems, and their relevance to any particular cyber defense task will require a lot of processing. If you just dumped all of this information into any agent, it would be overwhelming, and most of it would be irrelevant to the agent. Threat intelligence, again, vulnerability feeds, threat reports, lots of natural language, can be really high volume and requires processing to find the most relevant bits to the agent itself. And then mission objectives might be briefs, strategic priorities. These are challenging for yet another reason, in that they typically require a very long time planning, can be quite dynamic. So you kind of have to do a lot of reasoning over these things to decide on what is relevant to the decision making of the agent. The core agent can't handle this kind of thing very easily. So these are the main benefits of this contextual translation framework. We can gain a lot of efficiency by passing off all this really complicated, expensive processing to specialist models that sit outside of the main RL loop. These can also kind of filter out noise, and that leaves you with a very small, lightweight response agent that does the actual decision making for any particular case. We can pass off any context and reasoning to models or humans, which are good at this sort of thing, and can kind of process that information separately, reason about it, and then pass the relevant bits to the core agent. And it also allows adaptability, because we can make different situations look the same to the core agent based on our intelligence and reasoning about these higher level concepts, which means we can adapt our core agent to new situations at test time by making them look the same. And then one other thing that is very useful we can do reward shaping and action masking. So if we know as experts what the correct thing to do in any particular context is, then we can just tell the agent to do that thing. Okay, so to test this approach, we used a cyber simulation environment called Primate. There's an open source version available now on GitHub. We tested this on a use case called use case 6. That consisted of a tactical military network, had around 80 nodes in it, and had kind of practical defense related things in it, like command post vehicles, etc. There's also multi-stage attacks that are built into use case 6. And these consist of different threat actor profiles which have different targets and attack strategies. Finally, the network is generally controlled by these green agent objectives. So these are kind of the high-level mission objectives that the network is there to achieve. And the goal is just to maintain the network so that these green agent objectives can be achieved. We learned 2 different types of policies on this problem. One is preventative. So this is where the agent can act from before an attack and onwards, so that it can either prevent an attack from happening in the first place or immediately mitigate it when it does occur, and then also mitigative policies. So that's when the attack is allowed to play out, and then the agent has to recover the network from that position. In this context, the contextual RL framework has the core observation that comes from Primate, which is environment observation, which consists of kind of the network traffic, node properties, etc. We add in the contextual information directly into the observation. So you can see down here, this is what the observations look like. They're basically big matrices of numbers. We add in the context just as extra rows in this matrix. And sometimes the mission context is relevant to the bits that are around it. Sometimes it's irrelevant. So sometimes it'll be, you'll have a node property and the context below it is directly relevant to that. But sometimes there's just general information, which is what this kind of thing is. We also did contextualized rewards based on the contextual information, just to accelerate the learning process. To test this, we used an algorithm called PQL, which is an RL algorithm we presented at Camless last year. The key bits of it are that it is model-based, so it learns an explicit model of its environment, and it uses uncertainty modeling. So it learns uncertainties over that model of the environment as well. And generally, it works very well for cyber defense tasks. You can see a few plots just here to give you an example of this. The top plot is the average reward achieved during training. So generally, higher is better on all of these plots. The orange line is PQL, which learns to solve this task after a couple of hundred episodes. PPO struggles even after 1,000 episodes. It improves a little bit at the start and then never gets better after that. The bottom row is the reward for one particular episode. You can see PPO in green experiences the attack and never recovers from that, whereas orange is PQL on a preventative policy. It drops a little bit when an attack happens, but then stable after that. Blue is PQL on a preventative policy, mitigative policy, where the attack is allowed to play out and then has to recover it. So the PQL can start acting from time step 60 and recovers the network. To test the contextual RL framework, we did 4 different experiments with different variants in them. So the first is with mission priority changes, so new databases admins added. The second is changes to the hardware and the network topology. The third is variations to the threat intelligence. Essentially, a new attack type is added that targets a node that's not been attacked before. And then the last case is just all of these things together. And I think the important thing to note with all of this is that these things are unseen during training. So the agent adapts to something it's not seen during training at test time. So this is the first experiment. You can see during training that it learns policy quite quickly. There's no red agents in this, so it learns to solve the task very quickly. And you can see in the bottom, this is at test time. The context is swapping every 20 episodes, and the agent's able to adapt to these new contexts and achieves different rewards. Essentially, there's higher rewards when there's no more database admins because there's more things happening on the network. And then there's just a little bit of background noise because there's other things happening on the network as well. But we successfully see shifts in agent actions based on context at test time, and it hadn't seen these contexts beforehand, so could adapt with it without any retraining. This is the example with targeting a previously untargeted node. Orange is PQL, and blue is a hard-coded human optimal policy. And you can see they achieve very similar performance up to noise. And then the same thing on a particular episode. They achieve basically the same performance. So again, our approach adapted at test time without any retraining to this new context and was as good as humans at that task. Here's the example with unseen hardware anomalies and the change in topology. Blue is our agent trained on these anomalies, and then orange is it not trained on these anomalies and adapting at test time. Again, there's very good adaptation. The performance up to noise is very similar between our algorithm and the one that was trained on it on this specific task. And you see the same thing down here. Performance is roughly similar, slightly different strategies in terms of recovering, but we see effectively the same performance whether we trained on this specific example or adapting at test time. And then finally, all of these things together, the top row is the context shifting every 48 episodes, and you can see successful adaptation between these contexts every swap. On the bottom, you see again a particular episode. Blue is our agent trained on these specific scenarios. Orange is adapting at test time, and we get successful adaptation again. So in summary, we've introduced this contextual RL framework for autonomous cyber defense, and that led us to be able to do the first known adaptation at test time to new operational context for cyber defense. And we did this while achieving near human performance on quite a diverse range of cyber tasks. Because of this, we think that a contextual framework or something like it is necessary for real-world cyber defense. We need to be able to adapt to these changes in operational context, and this seems to be a valid way to do it. So we would be interested in exploring this more and other people taking this work and trying to develop what this framework should look like in practice. It's going to take an industry-wide effort to try and encode all of this operational context in ways that are useful for contextual frameworks to operate on. So we'd like to explore that more in future work, and if anyone else is interested in working on that, then please let me know. Thank you for listening. I'll say thank you to my co-author, Pranay, who again did most of the work on this, and then also to our funders, DSTL, through Fraser Nash. Thank you.
Hi, thank you for the amazing. Hello. So thank you for the amazing talk. I had a question about the models. Are they representation-based models, or are they decoder-based models, or like LLMs and stuff?
So the models in the contextual component? Yeah, so the contextual parts in this project are actually mostly like hard-coded systems. We were just trying to prove the concept that the contextual framework is useful here. That's something we're interested in exploring in the future. I think there's many ways this could go. And like we might also want to think about where humans fit into this and kind of human expertise as well. So yeah, definitely a kind of research question for the future.
Thank you for the talk. Can you be a little bit more concrete or give some examples of the sorts of actions that the agent was taking?
Yeah, so there's kind of two classes of actions that the agent can take in Primate. One is on the node level, so it can do specific things to node properties. That can be like killing apps that are running, that sort of thing, and they happen at the node level. Then there's controls that happen on at like kind of the router level, which control information flow through the network. Basically, you can set like access control rules and say this node can talk to this node, and this node can't talk to this node, that sort of thing.
So that was a very cool idea. Do you think that the response time with an autonomous cyber defense system like that could be better than humans, or because of the agents and all that could take time? So
Yeah,
the meantime to respond and all that, could it do response?
Yeah. I think the core idea here is that we take all the heavy lifting stuff out of the main RL loop, so that there's kind of a lightweight agent left at the core of it, which is operating on the most up-to-date contextual information that it has available, plus the current observation from the environment. So that loop should be really quick. Like we can, if we really wanted to, we could push through like thousands of decisions every second. That other like heavier loop that sits inside the contextual part, that will run slower because we probably need to use like at minimum like LLMs or something like very capable LLMs to make some of those decisions and do that processing. So the idea is that that slower loop sits outside the main response loop. And then the most up-to-date information can be fed through to that core agent.
Cool. I think we have time for one more question if there's any questions left from the audience. One back there. Thank you. Can you describe the reward function a little bit more? Because in practice, the main challenge to autonomous agents in general tends to be the reward function, particularly RL in security and particularly RL in defense. And designing that reward function instead of deriving it, especially if you're not deriving the reward function, that becomes really intrinsic.
Yeah.
So it'll be interesting to discuss how you derive the reward function.
Yeah. So I agree this is a very hard problem to do really well. So Primate defines the reward through these green mission objectives. The more green mission objectives that are successful, the higher the reward at any particular time. If you're interested in digging into that, you can look at the code, like it's open source. There's more detail available on that. But that really is like very high level and simple. Actually pulling that objective through into like meaningful learning is harder, and that's where some of the contextual rewards come in. So sometimes we know roughly what the right actions are, so we can reward those actions. Or we know like certain strategies that might work, so we can design reward functions around those specific cases. But yeah, in general, it's a hard problem, and it takes a while to learn from those kind of high level mission objectives.
Thank you so much. Everyone, we give another round of applause for it.